In our lecture 8.1, we have seen about the brief introduction about the structural analysis, and lecture 9.1 we have seen the difference between the static and dynamic analysis. And our last lecture we have seen that what is linear analysis and what is non-linear analysis. And today's topic is there are different type of non-linear analysis we carried out in our daily basis civil engineering design. So that we will see one by one. So that depends upon that when we should use that non-linear analysis and what type of non-linear analysis required. So all those things we will see in briefly. So when a structure is analyzed for a linear elastic behavior, the analysis carried out on the basis that the proportional relationship exists between the load and displacement. That means the linear material sustain relationship is exist. That is the main assumption. And another one is the geometric displacements are small. It should be within a limit. And the third is the boundary condition will not change with the structural deformation due to the external loads. So from the throat analysis, there should not be any change in the boundary condition. These three are the main important assumption for the linear analysis. If suppose when the load is exit the limit, so this linear sustain is no more valid, so then we have to go for non-linear material analysis. When the displacements are exceeding the limit, then we should go for the geometric non-linear analysis or the large displacement analysis. And when the boundary conditions start changing, we have to go for the boundary non-linear analysis. That we will see one by one. In a material nonlinear analysis, the behavior are encountered when the relatively big loadings are applied to the structure, thereby resulting in high stress in the range of the plastic region. So that proportional relationship is no more valid, so we have to go for material nonlinear analysis. So in material nonlinear analysis, that stress and strain, that relationship is given by a curve instead of a single value. In a linear analysis, we have used just a Young's modulus. There are no need to define the curve, but in nonlinear analysis, that nonlinear material analysis, we have to define this curve to do the analysis. So this define what happened once the load exit the limit into the elastic region. So accordingly, it will calculate the Young's modulus and it will be accounted in our analysis. So the second one is the geometric nonlinear analysis. In the geometric nonlinear analysis carried out when a structure undergoes large displacements and the change of its geometric shapes leads to nonlinear displacement strain relationships even in the elastic limit. So that geometric displacement should be small. That is the one another important assumption for linear analysis. If the displacements are very high, so we cannot use the conventional linear analysis, we have to go for geometric nonlinear analysis. So cable stayed structures such as this is a suspension bridge, another cable stayed bridge, so that are the one of the example for the nonlinear geometric analysis. In this case, suppose if the load is applied here, originally the cable will be something look like this green color shown, right? Something like this. When the load is applied here, this pylon will move towards inside and this cable will go down. And if there is a non-loading approach spans, that cables will go up. So that is the final diagram will be the original one. The green color line represent the unloaded condition. So in this case, if you see that geometries are too much changing, so the coordinate of the element is keep on changing. So here we cannot use the linear elastic analysis. Here we should go for the geometric nonlinear analysis. So the importance of the geometric nonlinear analysis is a geometric nonlinear analysis must be carried out if a structure exhibits a significant change in its shape under the applied load, as we have seen in the suspension bridge. So resulting the large displacement change the coordinate of the structure or the additional loads like moments are induced. So this additional load or moment, how it is induced. So the P delta analysis on type of geometric nonlinearity. If you see here, the load horizontal load H is applied at this level and the vertical load V is applied here. So due to this combined effect of this loading, the structure will deform as shown here in the dashed line. So due to this, what would be the moment will come here usually. So this H is having a span of L, and this is deformed to a small distance E. So the actual moment is this H into L if we ignore the geometric nonlinearity. So the additional moment due to geometric nonlinearity will be this V load is moved towards this side distance E. So V into E is the additional moment. So the total moment is H into L and V into E. So this additional moment V is we have to account if in case of the geometry is deformed too much. So in a computer program, how it is accounted? In a computer program, usually we used to have this K stiffness, use the deformation matrix, and P is the external load matrix. So in addition to this, the Kg is the geometric stiffness matrix resulting from the member force and stresses at the each step of iteration. Actually, this is a iterative process. Actually, once the load is applied, so this geometric stiffness will be arrived, and in the second iteration it will check the convergence limit. So if the convergence is happened, the iteration will be completed, the analysis over, the final result we will get. Suppose if the convergence is not meeting our requirement, then again what it will do, keep on analyzing each every at the end of the each iteration. So this kg will be updated. This k is always constant. K is the stiffness matrix of free deformed model, this original model, and this kg is the one variable matrix, and this is the called geometric stiffness matrix, and p is the static load vector, and u is the displacement vector. The third is the boundary nonlinear analysis. The boundary nonlinear analysis of load displacement relationship can occur in a structure where the boundary condition changes with the structural deformation due to the external load. For example, the compression only spring is conditioned in a structure contact with the soil. Foundation is a one example for the boundary nonlinear analysis case. In this case, due to whatever the load applied over this area will go to soil through the side walls. Since here the foundation is in the form of again a base slab, so when the load is applied this way, it will get the reaction from the soil near to the wall. So due to this, sometimes the soil is too hard. Here the soil very near to the side wall will take all the load. So due to the upward deflection, there will be some contact loss between the structure and the soil. If the soil is poor, so this everywhere it will connect. The soil will deform according to the slab bending shape. So everywhere there will be contacts, and there is no loss of contact at the time, no problem. Sometimes the soil is very poor, this will happen. So you can clearly see here and all there is no contact between the soil and the structure. So this is, so when at the time of analysis, initially what we will do, this boundary condition will not change. That is another one important assumption for linear analysis. Since here it is changing, we have to go for boundary nonlinear analysis. This is the example for the boundary nonlinear analysis. So at the end, if you see here, some here all the nodes are having some soil spring to represent the soil. So if you see, some reactions are positive and some reactions mid here are negative, as we have seen in the previous slide. Like here there is no contact, so here it should not take any reaction at all, but soil cannot take tension. It can resist only the compressive force only. When structure is hit, supported over a soil, wherever it has the contact, then only it can take some loads, but it cannot take the contact loss area, so it cannot take any tension. So to do the correct analysis, what will do, at the beginning of the modeling we have to consider all the base law node with the compression only spring. At end of this is the iteration 1 result. What we are seeing here is, if you see here, we have to check whether all the reactions are positive or negative. If suppose all are positive, that analysis is over, no need to go for any iteration. Suppose few reactions are negative, then the supports having the negative reactions will be removed in the second analysis, and only this 4 and this 4, this 8 node going to have compression only spring. Again, this after analysis, the result we have to compare again whether all the reactions are positive, then it will go and stop, otherwise this loop will continue till the end. So this is how the computer programs works. Summary. So the type of non-linearity. So one is non-linear material non-linearity, material that don't have the complete linear sustained curve, and the geometry non-linearity, changing the shape of the model when the large deformation exists, and the non-linear boundary condition that involve the component contact with the soil. And the another one, nonlinear analysis, the loading condition. Here the loading means creep and shrinkage. Usually creep and shrinkage is a not short time loading, it is a long time loading. It will be there in a throughout life, maybe 100 year. If you are designing a structure, it will be there forever. So that and all comes under nonlinear analysis only. All the whatever the analysis we are doing stage, in if you have seen in the commercial app, there will be option to do a stage analysis, stage 1, stage 2, stage 1 foundation construction, stage 2 superstructure erection, stage 3 external superimposed load fixing, and stage 4 maybe service condition. So if whatever the, since if you see that the sequence, every stage there will be some change in the element or sub boundary condition. These all are called non-linear analysis only. We cannot call it as a linear analysis.